the angle of departure concept, let us look at one example. So find angle of departure of the system whose open loop transfer function is given by GH of S is equal to K divided by S into S plus 6 into S square plus 4S plus 13. So for this problem we need to calculate angle of departure. So once the open loop transfer function is available to you, immediately look at, do you have any complex poles in the system? So complex open loop poles. So in this particular system, S square plus 4S plus 13, if you find the roots of the quadratic, then you will be getting minus 2 plus or minus J3. Means, so you will have complex poles for this system. So if you have complex poles, then only you start calculating angular departure. Otherwise, simply you say that since there are no complex poles in the open loop transfer function, you need not calculate, or there are no angle of departure. A single statement is enough. Now, since it is there, we'll look at how to calculate angle of departure. So the first step is write what are the poles and zeros available. In this case, there are no zeros at all, only we have poles, and there are 4 poles available. And what are the pole locations? If you look at the denominator, you can find out the poles. S is equal to 0 and S is equal to minus 6, S is equal to minus 2 plus or minus J3. Locate these poles in S plane. So when you locate S plane, and one pole at origin, one pole at minus 6, and one pole minus 2 plus J3, and another pole minus 2 minus J3. So I have 4 poles like this. So angle of departure we will calculate first for the pole which is available here. So at this pole I want to calculate phi d, that is angle of departure. Now from this pole you draw the vectors to all other poles and zeros. So from this pole I am going to draw the vectors to this pole and origin pole and also this pole, 3 vectors, and there are no zeros at all. Therefore I have 3 vectors. Now measure the angles from right side to the vector. So the angles always to be measured from the right side, right? If you have a vector here, we should take from the right side. This vector you have to take it from the right side, and here also I have from take it the right side. So I just name it. What are the angles? So this angle is phi p1, and this angle is phi p2, and this angle is phi p3. Let us see how to calculate it. So if at all, if you locate these poles and zeros in a graph, a linear graph, so you have all a grid, so you know all the values, exact values. So you can locate them and take the scale, you draw the vectors, and using protractor you can measure the angles if the scale is available, if that graph is available. So generally we are going to draw root locus on linear graph only. So without graph also we can calculate analytically using the trigonometric laws. It's very easy. Now phi p1, what is phi p1? To get the phi p1, let us take this triangle. So what is this triangle? I have this length is 3 and this length is 2, right? And this angle will measure 180 minus that angle will be phi p1. So we can write it as a phi p1 is equal to 180 minus tan inverse of 3 by 2. So tan inverse of 3 by 2, 180 minus of this, that gives us one angle phi p1 as 123.7. Similarly phi p2, then you can take directly angle phi p2 is tan inverse of 3 by 4. So tan inverse of 3 by 4, it comes around 36.86. And the third one you need not calculate because it is exactly right angle, so it is 90 degrees. So phi p1 is 123.7, phi p2 is 36.86, and phi p3 is 90 degrees. Then we can write what is your phi d. What is phi d? Phi d is nothing but 180 minus, we should open the bracket, so phi p1 minus phi z1. So phi p1, all the angles of your poles to the complex poles, and phi z is all the angles from all other zeros to the complex pole. So zeros are not there, so 180 minus, then you can add all the angles, 123.7 plus 36.86 plus 90, and you will get this as your phi d is equal to minus 70.86. So what is this minus 70.86? So this is the angle at which your complex pole, at this complex pole, root locus branch will leave the complex pole, right? So what is a root locus branch? Basically root locus branch will start at pole at it ends at 0 or infinity. So when k is increasing, so your root locus branch has to move, your closed loop pole has to move from this point to, so anyway, any direction depending upon the 0 location, depending upon the asymptote. So when it is taking out, when it is coming out from that, at what angle it is coming? So in this problem, that minus 2 plus j3 pole will take the angle of minus 70.86 while it is coming out of the that particular complex pole. Once this is phi d is available, we have another complex pole here. So you need not calculate which is a minus of that value. So your phi d is equal to minus of minus, that will be 70.86. So this way we can calculate angle of departure. What is angle of arrival? So it is the angle at which one of the root locus branches terminates at the complex 0. So terminating is arriving. So at complex 0 my root locus branches are going to be end up, therefore it is ending at what angle it is going to end, that is the angle of arrival. And from this very clear, if you have complex zeros in the open loop transfer function, then only we should calculate angle of arrival, otherwise the calculation is not needed. What is the formula? Phi a is equal to 180 plus phi. So phi d is 180 minus phi, here it is 180 plus phi. The phi definition is same. What is phi? Sigma phi p minus sigma phi z. What is sigma phi p definition? Sum of the angles vectors drawn from all other poles to the complex 0, because arrival is to the complex 0. Then what is sigma phi z? It is sum of the angles for the vectors drawn from all other zeros to the complex 0. So you draw the vectors, measure the angles, then substitute in the formula to get the angle of arrival. Let us take one example. So your gh of s is equal to k into s square plus 4s plus 13 divided by s into s plus 6. Find angle of departure for this system, angle of arrival for this system. So angle of departure is not possible because we don't have any complex poles. We have only complex zeros. I just locate them. Problem is same, only that quadratic term is taken into numerator, that's it. So location of poles are same. S is equal to 0, 1, S is equal to minus 6 is on real axis same. So complex, previously it was pole, now it is 0 here, 0 here. Now for this complex 0, I need to calculate angle of arrival. So at what angle it is going to terminate the root locus branch at the complex 0. So from this you draw the vectors, right? Then we can measure the angles. So when you are measuring the angles, before that you should name the angles. So from this complex 0 to the origin pole, this is phi p1, the calculation is same, you will be getting it as 123.7, and the another pole here phi p2. So since all the values are same, the angle measurement is also same, it is going to be 36.86, but this is complex 0, right? So complex 0 is 90 degrees, therefore your phi z1 is 90 degrees. What is the formula now? Phi a is equal to 180 plus, first I should take sum of the angles from the pole, that is 123.7 plus 36.86 minus sum of the angles of zeros, that will be minus 90. So if you do this, you will be getting phi a as minus 109.44. So this is the angle at which your root locus branch will terminate at the complex 0. What about the other complex 0? Again it is a minus of that value. So phi a star, star indicates the complex conjugate of that is plus 109.44. So this way we can calculate angle of arrival. If at all if you have complex zeros in the open loop transfer function, then we can find the angle of departure if at all if you have complex poles in the open loop transfer function. Some complex systems you will be having both complex poles and complex zeros. So we have to calculate each and everything for any given open loop transfer function.